Now we will show you how to use equilibrium to find the tensions in the cables. The weight is hanging from a vertical cable. 2 additional cables are used so that the load can be supported from the side walls. All 3 cables are connected to a common ring. The weight W is known and the directions of all the cables are known. What are the magnitudes of the tensions A and B in the side cables? The first step is to choose an appropriate body or subsystem on which the forces, known and unknown, act. The cables, the weight, and the ring are all in equilibrium. The ring is a good choice since all 3 cables are attached to it. In the second step, we draw the free body diagram, clearly labeling all the attributes of all known and unknown forces. Forces exerted by cables act away from the ring in the directions of the cables. The forces exerted by the cables have unknown magnitudes labeled A and B. The magnitude of the force due to the vertical cord is equal to the suspended weight. Why? If we were to draw an FBD of the suspended weight, the only forces on it are gravity and the upward tension. To be in equilibrium, the tension must equal the weight. In the third step, we note if any equilibrium conditions will obviously be satisfied given the forces that are present. Then we compare the number of remaining independent equilibrium equations with the number of unknowns. Notice that the forces of the cables on the ring all run through the center of the ring. Therefore, the moment of all the forces about the center of the ring is obviously 0. The forces act in more than one direction, so we will have to write 2 equations of force equilibrium. The directions of all the forces are known, but the magnitudes A and B are unknown. So there are 2 independent equations of equilibrium and 2 unknowns. In the fourth step, we first decide how to efficiently impose the conditions of equilibrium. For force equilibrium, the decision we face is which system of axes to use to resolve the forces into components. In this and later examples, we will illustrate the benefits of different choices of axes. As our first choice, let the axes coincide with the horizontal and vertical directions. Now we apply the equations of force equilibrium along the horizontal and vertical axes. This requires us to resolve the cable forces into horizontal and vertical components, a skill that you learned in Module 4. We then solve these equations to find A and B. First, we rewrite the second equation to find B in terms of A. Then we substitute into the first equation to solve for A. Finally, we can use our rewritten second equation to solve for B. Let's consider now a different choice of axes. Notice that we can choose to define XY axes to be in any direction, not just horizontal and vertical. Say we choose XY axes so that the Y-axis runs through the force, B. We apply the equations of force equilibrium along the X and Y axes as we have now defined them. This requires us to resolve the cable force A and the weight into components along these axes. We then solve these equations to find A and B. Notice now that the equation along X has only one unknown A. This is the consequence of taking the Y-axis along B, so we can solve for A and then substitute back into the equation along Y to find B. This completes the solution to the problem.